Welcome back to the last video directly on dimensional analysis. But don't think this is the last time you'll see this concept. Dimensional analysis, or DA, as I like to call it, is a core skill for the RD exam. As you get closer to taking your exam, you'll learn about how the RD exam is broken up into 4 domains. Each domain has a different weight on the RD exam, but all 4 domains rely on dimensional analysis. Domain 1 focuses on the fundamentals of dietetics practice. So you'll use DA when working with basic ratios like cost per unit and when interpreting research data in units. Domain 2 focuses on community and public health nutrition, so you'll use dimensional analysis to calculate incidence and prevalence and percentages, as well as population-based measures and BMI. Domain 3 focuses on human nutrition and medical nutrition therapy, so you'll use dimensional analysis all over Domain 3. It's used in energy and macronutrient calculations, as well as enteral and parenteral nutrition, as well as conversions like percents and grams. And then Domain 4 focuses on food science and food systems. So you'll use dimensional analysis when scaling recipes and calculating yield, as well as determining cost per serving. So here's the game plan. There's 4 practice problems to try in this video. As I mentioned in the last part, pause the video when a new practice problem appears and try to solve it yourself first. Then press play again to walk through the solution with me. I'll be here with you the whole time. Okay, take a deep breath. Let's get started. This problem says you are quadrupling a recipe that requires 6 4-ounce portions of chicken breast. There's our given right there, 4-ounce portions, and we need 6 of them, and we need to quadruple this recipe. We're solving for pounds. How many pounds of chicken breast do we need? This is a dimensional analysis problem because we are converting our units from ounces to pounds. So we need to know the equivalent statement between ounces and pounds. We looked at this one in the last video. 1 pound is equal to 16 ounces. And so we can write this equivalent statement out as 2 fractions. Written as a fraction, these 2 equivalent statements mean the same thing, but we want the one that has units that match our equivalent statement. So we need 6 4-ounce portions. If it's okay with you, I'm just going to go ahead and multiply those and say we need 24 ounces of chicken breast. Where did that 24 ounce come from? It comes from the fact that we need 6 servings of 4 ounces. Now the problem wants us to convert to pounds. So whatever our given units are will automatically go in the bottom of the equivalent statement so that they cancel out. The units we're solving to go in the top. So we want this equivalent statement, the one that tells me pounds and ounces with pounds on the top and ounces on the bottom. 24 ounces times 1 pound per 16 ounces will cause my ounces to cancel out, and what we end up with is 1.5 pounds. But remember, this recipe says that we need to quadruple it. 1.5 pounds is to make one of these recipes. So since we are quadrupling this recipe, we need 6 pounds of chicken breast here. Shall we try another? This next one is a business application, and we'll explore this much more deeply in Module 9, but we'll also look at it again later in this unit when we talk about break-even pricing. But this example gives you a chance to practice using dimensional analysis in a new context that's not related to food service. It says, how many weeks, that's what we're solving for, weeks, will it take for an investment to pay the company back? So we're converting from dollars, $20,000, into weeks, and we actually have our equivalent statement hidden in the problem. Can you find it? Remember, try to pause this video and solve it on your own. Since it's a dimensional analysis problem, we're trying to convert from the given to what we're solving for using our equivalent statement. Well, the equivalent statement is right here. $267 in labor costs will be saved per week. Every week, it saves $267. So to write it as an equal sign, I would write it just like this. $267 for every 1 week. And if you want to write it out as 2 fractions, more power to you. $267 for every 1 week. Or we can write it the other way, that in 1 week, the company, due to this upgrade, saves $267. And so the given here is $20,000. Since dollars is in the top, we need to put dollars in the bottom so that they cancel out, which means we want this equivalent statement right here. Every 1 week, the company saves $267. Dollars will cancel out, and that means it will take 74.9 weeks for the company's investment to pay itself off, given that it saves $267 every week and it costs $20,000. This is called your payback period. And again, we will cover this in depth. But the point is, even outside of food service, dimensional analysis gives you a clear and structured way to solve real-world problems. Let's try another. This is another example that ties into administrative nutrition, and we will revisit this topic again in Module 9. But again, this is a direct application of dimensional analysis. Pause it. Try it on your own. The question says you buy 15 pounds of apples. It asks you to figure out the cost. That's why this is a dimensional analysis problem, because you're converting from pounds to cost. And we need to know the equivalent statement here. But again, this one is given to you in the problem. Did you find it? $1.39 per pound is our equivalent statement. And so my given is 15 pounds. Pounds will automatically go in the bottom of the equivalent statement, so they cancel out. And if you need to write this out as two fractions, $1.39 is the value of 1 pound of apples, or for every 1 pound of apples, you need to spend $1.39. They mean the same thing, but since we want dollars on the top, we need pounds on the bottom, we'll use this equivalent statement right here. Every pound costs $1.39, so if we need 15 pounds, that's going to run us $20.85. That's it. No need to overthink these. You identify the units, you apply the equivalents, and then the math just follows. So before I send you off to try these on your own, let's try one in the clinical world. We'll go deep into this in our upcoming lesson on enteral nutrition and TPN. But for now, let's see how dimensional analysis helps us build complex calculations with confidence. This problem says that we have a patient who needs 2,400 calories every day. How many milliliters of 1.2 kilocalorie per milliliter of enteral formula do they need in a day? How many milliliters should be administered per hour if the nutrition support is continuous? Take a breath, pause the video, try it on your own. And let's try to walk through it step by step. This is a dimensional analysis problem that wants you to convert from calories into milliliters of formula. The given in this problem is 2,400 calories per day, and we need to convert into milliliters. So we need to know the equivalent statement between calories and milliliters, and that's given to us right here. It's an equivalent statement that's already written as a fraction. But actually, there's two equivalent statements that we need here because the problem also says how many milliliters should be administered per hour. So we need to know the number of hours in a day. Let's just get them both down. 1.2 kcals is equal to 1 milliliter. That's this one right here. It was written as a fraction. It was written as 1.2 kcals is the amount of energy in every 1 milliliter, which means it stems from that equivalent statement. And so we could also write it this way. In every 1 milliliter, you would be giving 1.2 kilocalories. We'll work with that other equivalent statement in a minute because we'll deal with every conversion separately. Let's first convert from calories into milliliters. The given is 2,400 calories per every 1 day. And now we need to know the relationship between milliliters and kilocalories. Every 1 milliliter has 1.2 kilocalories in it. And so if we have 2,400 kilocalories that we need to meet every day, then the amount of milliliters of enteral formula that we need to provide is 2,000 milliliters per every 1 day. And that's the first problem, a straightforward application of dimensional analysis to find the amount of milliliters we need to provide in a day. But the second part of this problem says how many need to be administered per hour if it's running 24 hours a day. So every 1 day is 24 hours. We can write our equivalent statement this way, or we can write it this way. We want to convert from days now into hours. So we want to get rid of this unit on the bottom right here. In order to get rid of that unit, this one is a little bit different than what we've seen before, but it works on the same principle. That unit needs to go in the top so that they cancel out. We know that in every 1 day, there are 24 hours. So we're just going to plug this equivalent statement in right there. Every 1 day is 24 hours. Days cancel out. And if you take 2,000 milliliters, multiply it by 1, and divide by 24, you'll get 83 milliliters per hour. This is a direct clinical application of dimensional analysis, and you'll be doing this kind of calculation often, especially when we get into our lessons on enteral and parenteral nutrition. Dimensional analysis is one of those skills that the more you practice with it, the better you get. So keep on practicing it. Follow your units. Write out your equivalent statements as 2 fractions until you get good enough that you can see them in your head. And reach out for support. You are not in this alone. Good luck studying, and I will see you in the next one.